Okay, so in this video I'm going to go over quantitative heat problems, different from the old one, or from qualitative. So quantitative means dealing with numbers. We're going to actually quantify this stuff, put it into joules. So there are several formulas that you're going to need to know. For Chem 1-2 you're going to be given these formulas, you'll be given the constants. So let's go through all these formulas and constants now. So you should write these down if you're watching. Keep it on a sheet next to you because you'll be able to use these to answer the problems. So we have, let me just do a little intro here. There's 5 steps on heating curve. Okay. Each step is going to have its own formula. Okay. For all of these steps that go up, temperature is actually changing. The basic formula for this step and for this step and for this step is going to be Q. Let me do an uppercase Q for that. I always mess that up. Q equals MC delta T. Let me just copy that down again. Equals MC delta T. Q equals MC delta T. Now, Q means heat. Let me write that up here. Q equals heat, and the unit for that is joules. Okay. M is mass, and in this case mass has to be in grams. You'll see why in just a minute. Let's skip C for now. Let's do delta T. The triangle is the Greek symbol for delta, or it is Greek symbol delta. It means change in. So delta T means change in temperature. Change in T for temperature, and that has to be in degrees Celsius, not Kelvin. Don't get mixed up with your gas laws. Celsius. And finally, C. C is your specific heat capacity, which is sometimes just called specific heat, but specific heat capacity. And the unit for this is joules per gram degree Celsius. What this measures is how much energy it takes to raise 1 gram of a substance temperature by 1 degree. So let's say I have 1 gram of water, just tiny little couple raindrops. 1 gram of water, and let's say it's at 30 degrees, and I want to heat that up to 31 degrees. I'm going to have to give it energy. Well, how much am I going to give? That is determined by the specific heat capacity. And the unit has to make sense here. It's going to be how many joules per gram per degree Celsius. So don't forget these units, joules per gram degree Celsius. And specific heat capacity is always going to be given to you. Okay. Now, specific heat capacity changes whether you're talking about a solid, liquid, or gas of the same substance. It also is drastically different in different substances. So the way we distinguish this is we say C1 for solid, C2 for liquid, and C3 for gas. These are 3 different values that we're going to use. Okay? On a different slide, I'm going to post those C values. Make sure you write them down. You'll be given them on tests and quizzes. You don't have to memorize these. Okay? And I'm also going to clarify that this is just for water, really H2O. You know, most of the problems we deal with involve H2O. So for H2O, C1, which is solid, equals, and let me make sure I have these memorized from last year. Yes, 2.10 joules per gram degree Celsius. C2, which is liquid, equals 4.18 joules per gram degree Celsius. And C3, which is gas, is 1.90 joules per gram degree Celsius. Okay. Now these are sort of estimates. In fact, the colder something is, this actually I believe drops, and the hotter something is, that also, well, it will change. I'm not sure if it goes up or down. But anyway, these are estimates, so if you're looking this up in like a textbook or online, you might see slightly different values, but these are the ones that we're going to be using. So again, what this means is if I have ice, let's say I have ice at like -10 degrees, if I want to increase the temperature by 1 degree Celsius, if I have 1 gram of ice by 1 degree Celsius, I need 2.18 joules. If I have that same 1 gram, but now it's liquid, and I want to increase its liquid temperature by 1 degree, I need 4.18 joules. So it's pretty much double. You need almost twice the amount of energy to increase the liquid temperature as opposed to the solid temperature. Anyway, these are our C values, and that covers 3 formulas. The other 2 formulas deal with these plateaus here. Because if you think about it, when you're on the plateau, there is no delta C. So if you multiply by 0, it's just going to give you 0. So we need separate formulas to show how the temperature changes, not how the temperature changes. You need to show how much energy goes into freezing or melting, how much energy goes into boiling or condensing. So the formulas for these plateaus, it is Q equals M times the latent heat, which I use the symbol L most commonly. This is also going to be called H. Okay? Same for here. Q equals M times the latent heat. Now when I say latent, that means hidden. Latent means hidden. And the way that comes about is if you're like heating up some water. I mean, think back to the Icy Hot Lab. We had those hot plates cranked up, and we were trying to melt ice. We were clearly putting energy into the system, but the temperature stayed at 0. So much that like most of the groups in my class were saying, I think this is broken, the temperature's not going up. Well, energy was going in, but where did that go? It was hidden. It was hidden, technically it was breaking, it was spreading apart the molecules, changing their arrangement. So anyway, that's where the L comes from. And again, to distinguish between these two, we have to clarify that this is melting, which is also known as fusion. So we say LF. So mass times the latent heat of fusion. And here, Q equals mass times the latent heat of vaporization. Vaporization, that's this phase change, liquid into gas. Okay? So these are our 5 formulas. Sometimes you'll see it written as like A, B, C, D, and E. So this is A, this is B, this is C, this is D, and this is E. And before we go on, last thing I have to define is what are these 2 values. So let's go back to our constants. Again, this is just for H2O. If we deal with a different substance, I'll tell you what these values are. So the latent heat of fusion of water is 334 joules per gram. Notice no delta T in there, or no degree Celsius. That's because there is no change in temperature during a phase change. So what this means is if I have 1 gram of ice and I want to melt it, which is what fusion is, I need to put 334 joules in. And that's a lot. I mean, if I took that 1 gram of ice and wanted to increase its temperature by 1 degree, all I need is 2.10 joules to make it go up by 1 degree. If I want to melt it, I got to put 334 joules in. And you'll see that's nothing compared to vaporization. LV shows latent heat of vaporization. This is going to be a lot higher. 2,260 joules per gram. This means that if you have 1 gram of hot 100 degrees Celsius water that's ready to boil, 1 gram requires 2,260 joules just to boil, just to vaporize. Okay? Now remember, these are just for H2O, but these are the constants you'll be given, and these are constants that we're going to have to use. So plenty of stuff, plenty of new information. Make sure you jot all this down, and let's start our problems. By the way, these problems come off of this sheet that I will give my students. Other teachers may give the same or similar version. I call it heat problems, and this is my list of 18 problems. I do have an answer key with it, but if I recall from last year, there might be a couple errors on it. So I'll hopefully catch those if they are on these problems. But even if you don't have the worksheet, I have all the problems listed, so just pause the video, try to work out the problem, and then follow along. Number 1, calculate the amount of heat given off by 192 grams of water as it cools from 81 to 42 degrees Celsius. So when the water cools down, it has to give off heat. We're going to find how much. Well, first let's identify what segment we're working on, and that'll tell us which formula we need to use. So I have water from 81 to 42. Now we're cooling. So let's draw our cooling curve like that. Not very accurate. Let me do that again. 1, 2, 3, 4, 5. Okay? So I have water at 82, which is right about here. It's ending at 42, which is right about there. So I'm confined just to level C, just this middle part. So the formula here, if you go back, Q equals mC2 delta T. Now that C2 is the liquid specific heat capacity. Okay, so this is the only formula I need, and we're looking for the amount of heat, which is Q. So I accidentally put the lowercase q. I believe it should be uppercase, but in this context it really doesn't matter. So Q is mC2 delta T. Let's plug in our values. Q equals, mass is 192 grams. C2, you look up on your sheet, 4.18 joules per gram degree Celsius. Delta T, that's the change in temperature. Now this is always going to be positive, even if you're making it less. I don't want to enter negative value for this, because there's really no such thing as negative joules. I mean, if you get negative joules, it just means that it's positive joules are being released. But what I prefer to do is keep all of my delta T's positive, which keeps all of my final answers positive. So 81 minus 42 is 39, right? Yes. So delta T is 39 degrees Celsius. Before I solve, let's check our units. Gram cancels gram. Degree Celsius cancels degree Celsius. What am I left with? Joules. That makes sense. I'm looking for joules of heat. Q equals 192 times 4.18 times 39. Okay, I have my answer, but I'm going to look at sig figs here. In this case, back when we were doing gas laws, you would turn that into Kelvin and use 3 sig figs. But for this sake, we're just using 2 sig figs here. I'm going to give this 2 sig figs. I see 31,299.84. I'm going to say 31,000 joules. Final answer, 2 sig figs. Yep. Next, problem number 2. I'm only going to do about 5 or 6 of these, by the way. I'm not doing all 18. 2 says, calculate the amount of heat needed to completely boil 200 grams of water. Okay, so let's see where we're starting from. We're now boiling, so we're going to be going up a heating curve, 1, 2, 3, 4, 5. And since it just mentions boiling, we're going to assume that this water is already boiling. It's not like it says how much heat is required to boil 200 grams of room temperature water, because that would imply we have to take it up to 100, then boil it. So here I'm just going to start right here, and I'm going to boil it until it's gone. So I'm just dealing with one segment again, segment D. Now the formula for this, Q equals M times the latent heat of vaporization. Again, you might see an H here. Q equals MHF. Depends on your teacher, it means the same thing. If you look in 2 different textbooks, it could tell you 2 different things. So you really should know both. Q equals M times latent heat of fusion. Mass is given. Q equals 200 grams. Latent heat of vaporization, you look up on your form, 2,260 joules per gram. Gram cancels gram. We're left with joules. Does that make sense? Yes, it does. 200 times 2260 equals, okay, and I have my answer here, but I want to check sig figs. I'm seeing 3 sig figs here with the dot, so I'm going to give this 3 sig figs. 452,000 joules. Okay. Joules are very small, actually. A joule of energy is tiny. Let's just see, does that make sense? Yes, it does. Next problem, number 3. What mass of ice could 824,000 joules of energy melt? All right. Well, let's draw our heating curve. 1, 2, 3, 4, 5. Okay, so let's see where we're starting from. Now we're starting with ice, but I don't tell you anything about a temperature, so I'm not going to assume it starts anything less than 0. I'm just going to say it's starting as 0 degree ice. It's ready to melt, and I'm going to be giving it this many joules. So again, I'm just going to kind of stick on this plateau until it completely finishes, or until I run out of energy. So the formula for segment B is Q equals mass times the latent heat of fusion. And what am I solving for here? What mass of ice? So let's rearrange this for M. M is going to equal Q divided by LF. Plug in 824,000 for Q. And I'm going to put my joules here. Latent heat of fusion, that you would look up again, 334 joules per gram. Now with the units here, numerator joule cancels denominator joule. And then here I have the inverse of the inverse, which basically means that gram's going to pop out back on top. And that's the unit I'm looking for. So 824,000 divided by 334. Let me look at sig figs. I'm seeing 3 sig figs here, so I'm going to report 3 sig figs. I see 2,470. And my unit is grams. Yep. Next problem, skip number 4. So here's number 5. Okay. When you solve for the final temperature, those are always a little bit trickier, so make sure you're careful with these. 5,100 joules are added to 141 grams of 5 degrees Celsius water. What's the final temperature? Okay. So I have 5 degrees Celsius water sitting here. Now that's very close to freezing. But I'm going to be adding heat to it, so it's going to get warmer, not colder. So what's the final temperature? Let's chart this on my heating curve. 1, 2, 3, 4, 5. So I'm starting with 5-degree water, which puts me right about here. And I'm going to be heating it, which just means I'm going up here somewhere. Now based on the phrasing of the question, it doesn't say anything about boiling, or it doesn't say like what's the final temperature of the gas, so I'm just going to assume that it's going to stay as a liquid. In fact, I know that 5,100 joules, that's pretty much nothing. So we'll see how much it goes up by. So I believe I'm going to stick here in the C range, which my formula is Q equals mc2 delta T. The problem says, what's the final temperature? Well, I don't really have a final temperature in here. I mean, technically you could call delta C T final minus T initial, but I think that confuses it more. What I prefer to do is this. Let's just solve for delta T as a unit, or as a symbol. And then once we get delta T, we can just add it to my 5 degrees Celsius. So let's rearrange this and solve for delta T. So I'm going to divide everything by both sides by this stuff. So I'm going to get delta T equals Q over mc2. Let's plug in our numbers. Q is 5,100 joules. M is 141 grams. And C2, you look up on your worksheet, is 4.18 joules per gram degree Celsius. Let's check our units. Joules in the numerator cancels joules in the denominator. This gram is going to cancel that gram because it's numerator denominator. I'm left with degrees Celsius as my double denominator. It's the inverse of my inverse, so that's going to pop back out on top, which I want. Let's do the math. 5,100 divided by 141 equals, divided by 4.18 equals, and with, let's see, I guess with sig figs I'm looking at 1 sig fig here, but technically I'm adding, so I'm not going to limit myself to that, because when we add numbers we don't look at sig figs. For sig figs I'm looking at 2 here and 3 here, so I'm going to give my answer 2 sig figs. 8.7 degrees Celsius, and that equals delta T. Okay, change in temperature is 8.7. Well, I'm not asking for the change in temperature. I'm saying what's the final temperature? Well, I started at 5, so it's either going to go up by 8.7 or down by 8.7. So you look for clues in the problem. Well, since here I say these joules are added to water, I'm going to add the heat. I'm going to make the temperature go up. If I said these were removed from water, then you would subtract. Okay? So in this case, I'm going to say 5 plus 8.7, which is going to give me 13.7. However, when we add numbers, we don't look at sig figs or anything like that. We look at decimal places. So here I have 0 numbers after the decimal. Here I have 1. So I'm limited to 0 numbers after the decimal. In other words, I'm limited to the nearest whole number. So I'm going to call this 14 degrees Celsius. And that's my answer. That's the final temperature. Okay, yep. Couple more problems. 14, so I'm jumping a lot of numbers, so this one's going to be a little trickier. What's the total energy given off when 68 grams of 112 degrees Celsius water vapor cools into 80 degrees Celsius water? So I'm starting with water vapor, 112. It's going to turn into 80 degree water. But remember, it's not just one step. There's actually 3 steps here. Let's draw our heating curve. So this is cooling, so let me actually change that cooling curve. 1, 2, 3, 4, 5. And I'm starting with 112 degrees Celsius water vapor. This is 100, so I'm starting right about here. And it's going to cool down into 80 degree water. So looking at the steps here, I have step 1, I have step 2, and I have step 3. If we were doing LOLs, you'd be doing 3 LOLs in this. Same thing with these heat problems. We're going to do 3 different steps. There's 3 formulas. My first formula, Q equals mc3 delta T, C3 being gas. Second formula, Q equals m times the latent heat of vaporization. Now technically it's not really vaporization, it's the opposite, it's condensation, but we still use this constant. Because instead of it being how much heat's required to boil it, now we're saying how much heat must be dumped off in order to condense it. Third formula right here, Q equals mc2 delta T. Each step has its own formula. What we're going to be doing, we're looking for what's the total energy given off. So find this much energy, find this much energy, find this much energy, add all 3 together. That's going to be our problem. So let's do this one first. Q equals mc3 delta T. Mass is 68 grams. C3, you got to look that up. It's 1.90 joules per gram degree Celsius. And delta T, careful here. We have 112 going into 80, but that's not step 1. Step 1 is just from 112 degrees down into 100 degrees. It's not going to jump right to 80. It has to stop at 100, condense, then drop down to 80. So my first delta T is only going to be 12 degrees. That's my first formula. Let's solve for Q. Well, before I do that, let me do my units. Gram cancel gram. Degree Celsius cancels degree Celsius. We're left with joules. That makes sense. 68 times 1.90 times 12 equals 1,550.4. You might be saying, why didn't you do sig figs? I'll do that at the end. I always like to do sig figs at the very, very end of the problem. Okay, so that's the joules that are given off as that 112 degree gas cools down to 100. Next step. Next step is that 100 degree gas is now condensing in a 100 degree liquid. Q equals m times the latent heat of vaporization. My mass was, what is that, 68? Yep, 68 grams. Latent heat of vaporization, you look that up, 2260 joules per gram. Remember, there's no no delta T in there because there's no temperature change during a phase change. Gram cancels gram, 68 times 2260. Q equals 153,680 joules. Again, don't worry about sig figs now. Take care of it at the end. Just comparing these two numbers real quick. To drop it down from 112 to 100 gave off just 1550. To then condense that gave off like, what's that, 10 to 100 times? Almost 100 times more. 153,000. What am I doing my basic math here? Divided by 15. Yeah, about 100 times more. So it just shows how much energy it takes to change the state of water. Anyway, we're not done. Final step. I now have 100 degrees Celsius liquid. I'm going to drop that down to 80 degrees Celsius liquid. I need to see how much heat's given off. Q equals mc2 delta T. 68 grams times C2, which is 4.18 joules per gram degree Celsius, times my third delta T. Now again, be careful. Don't say 112 minus 80. Don't say 32 degrees. In step 3, it's starting at 100 and it's dropping down to 80. So we're going to say 20 degrees. And I would say 20 point degrees Celsius, just so you don't accidentally limit yourself in sig figs. 20 degrees Celsius, gram cancels gram, Celsius cancels Celsius, we're left with joules. Let's get our final answer. 68 times 4.18 times 20. Again, not going to round off sig figs yet. 5684.8, and that is joules. So I figured out how much energy is given off in step 3, how much energy is given off in step 2, how much energy is given off in step 1. I'm going to add all 3 of those up, and then I'm going to finally limit my sig figs. Now, I know you might be saying, wait, didn't you say when you add things you don't look at sig figs? Yes, but in this case, the numbers I'm adding are technically not rounded off to sig figs yet. So what I'm going to do is look at my sig figs here. I'm going to say 2 sig figs, I see 2 sig figs, and I see 3 sig figs. What I'm going to do is limit myself to 2 sig figs as my final answer. So, 1550.4 plus 153680 plus 5684.8 gives me a total of, choose a different color here, 2 sig figs, 160,000 joules. Final answer, 160,000 joules. Okay. Last problem I'm going to go through is number 17. 252,000 joules of energy are added to 100 grams of 75 degrees Celsius water. Does all the water boil? If so, what is the final temperature? Alright, this is definitely going to be a tricky problem, so let's work it out. So I'm starting with, first of all, I'm adding energy, so we need a heating curve. And I'm starting at 75 degrees Celsius water right here. I'm going to be adding a whole bunch of joules to it. Does all the water boil? So first of all, that's implied that it's at least going to reach boiling. So here it's going to start moving across, and I'm going to even put like a question mark. Is it going to completely go across? I don't know. We're going to have to figure that out. If so, what's the final temperature? So it could even go up this high. We don't know. So this one we're going to have to kind of piece together along the way. So, first thing I have to realize is that by taking it at 75, what's my temperature? Yeah, 75 Celsius, I'm going to have to use some of this energy just to bring it up to 100. I can't just start boiling it off yet at 75. Unless, of course, I'm at an altitude where the pressure does so. I probably should have said, full discretion, all these occur at sea level, so don't do any water boiling at 75 type exceptions. So I'm going to have to take some of this energy and use it just to get it up to 75. So my first step should be, how much of this do I have to waste just getting it up those 25 degrees? So that's going to start me on section 3. Formula for this is Q equals mc2 delta T. And I want to solve for Q here. Q equals 100 grams times C2, which is 4.18 joules per gram degree Celsius. And delta T is going to be 25 degrees. I'm going from 75 up to 100. So 25 degrees. (100) times 25 times 4.18. And again, I'm just going to quickly double check my units. Gram, Celsius, Celsius. We're left with joules. Okay. Same thing with sig figs, leave it till the very end. So what I'm seeing here, Q equals 10,450 joules. What that means is just to bring it up to 100 and get it ready to start to boil, I have to lose 10,450 joules. So what I'm going to say is this. I started with 252,000. I'm going to say 252,000 minus 10,450 means I only have 241,550 joules left to boil. So that's important. Step one is done. We've made it up to the boiling point. Now let's boil. So at this point, there's kind of two ways you can solve this. I can say, all right, well, let me take this many joules and see how many grams I could actually boil compared to my 100 grams. Or what I think is going to be a better way to do it is I'm going to say, all right, I have 100 grams of water that's now at 100. It's ready to boil, ready to go. Let's find out how much heat I need to boil that 100 grams. If I have enough, then I'll have to continue on. If I don't have enough, we're done. So, how many joules do I need to boil 100 grams of water? For that formula, it's letter D. Q equals M times the latent heat of vaporization, which is 100 point grams, that's my mass, times my 2260 joules per gram. That's my latent heat of vaporization. Gram cancels grams. This one I could do in my head. 226,000, 226,000 joules. So that's how many joules it takes to boil 100 grams. Let's compare this to how much I actually had available. And as I can see, I had 241,550. I only needed this much. So let's copy that number down again, 241,550. And I'm going to subtract this now. This is how much I had available. This is how much I'm going to have to waste to boil that. Let's see how much is left. 241,550 minus 226,000 equals 15,500 joules. And these are now the joules left over to increase the temperature of the gas. So now I'm dealing with a gas and I have just a little bit left over to crank that temperature up. Let's see how high I can get it. So now I'm dealing in segment E. My formula for this, Q equals MC3 delta T. What are we solving for in this problem? Well, initially I said, what temperature is it going to reach? So I'm looking for delta T. Let's isolate delta T here. Delta T equals, so divide by this, so Q over MC3. For Q here, I'm going to make sure to use this Q, because this is how much energy I have left over. 15,500 joules. So I want to see how far that 15,500 can get me. Divided by 100 point grams times C3, which is 1.90 joules per gram degree Celsius. Joule cancels joule, gram cancels gram. Degree Celsius is my double denominator, my inverse of the inverse. So that's going to pop back out on top. Let's solve. 15,500 divided by 100 divided by 1.90 equals, let me write this down, I'll look at sig figs in just a second, 81.84. Now, with sig figs, I'm going to go back to my original problem. I see 3 sig figs, I see 3 sig figs, I'm seeing 75 degrees Celsius water, but let me try to think, does that actually come into my calculation since I'm adding 25? Yeah, I'm going to incorporate that because I multiplied by the 25 here. So I'm going to limit myself to 2 sig figs in my final answer. I'm going to write 82 degrees Celsius. But what does this really mean? That's not final temperature, that's delta T. That's how much I was able to bring it up by. But it started at 100 degrees Celsius. I'm now going to be adding 82 to this for my final temperature. This giant problem, the final temperature is 182 degrees Celsius. That's the final answer. Okay? So that's how we solve these quantitative heat problems.